Reverse mathematics is a program in mathematical logic that seeks to determine which axioms are required to prove theorems of mathematics. Its defining method can briefly be described as going backwards from the theorems to the axioms. In contrast to the ordinary mathematical practice of deriving theorems from axioms, it can be conceptualized as sculpting out necessary conditions from sufficient ones. The reverse mathematics program was foreshadowed by results in set theory such as the classical theorem that the axiom Axiom und Lemma are equivalent over ZF set theory. Reverse mathematics is usually carried out using subsystems of second-order arithmetic, where many of its definitions and methods are inspired by previous work in constructive analysis and proof theory. The use of second-order arithmetic also allows many techniques from recursion theory to be employed. Many results in reverse mathematics have corresponding results in computable analysis. The program was founded by Harvey Friedman. A standard reference for the subject is General Principles. In reverse mathematics, one starts with a framework language and a base theory, a core axiom system, that is too weak to prove most of the theorems one might be interested in, but still powerful enough to develop the definitions necessary to state these theorems. For example, to study the theorem, every bounded sequence of real numbers has a supremum, it is necessary to use a base system which can speak of real numbers and sequences of real numbers. For each theorem that can be stated in the base system but is not provable in the base system, the goal is to determine the particular axiom system that is necessary to prove that theorem. To show that a system S is required to prove a theorem T, two proofs are required. The first proof shows T is provable from S. This is an ordinary mathematical proof along with a justification that it can be carried out in the system S. The second proof, known as a reversal, shows that T itself implies S. This proof is carried out in the base system. The reversal establishes that no axiom system S that extends the base system can be weaker than S while still proving T. Use of second-order arithmetic. Most reverse mathematics research focuses on subsystems of second-order arithmetic. The body of research in reverse mathematics has established that weak subsystems of second-order arithmetic suffice to formalize almost all undergraduate-level mathematics. In second-order arithmetic, all objects can be represented as either natural numbers or sets of natural numbers. For example, in order to prove theorems about real numbers, the real numbers can be represented as Cauchy sequences of rational numbers, each of which can be represented as a set of natural numbers. The axiom systems most often considered in reverse mathematics have defined using axiom schemes called comprehension schemes. Such a scheme states that any set of natural numbers definable by a formula of a given complexity exists. In this context, the complexity of formulas is measured using the arithmetical hierarchy and analytical hierarchy. The reason that reverse mathematics is not carried out using set theory as a base system is that the language of set theory is too expressive. Extremely complex sets of natural numbers can be defined by simple formulas in the language of set theory. In the context of second-order arithmetic, results such as Post's theorem establish a close link between the complexity of a formula and the computability of the set it defines. Another effect of using second-order arithmetic is the need to restrict general mathematical theorems to forms that can be expressed within arithmetic. For example, second-order arithmetic can express the principle, every countable vector space has a basis, but it cannot express the principle, every vector space has a basis. In practical terms, this means that theorems of algebra and combinatorics are restricted to countable structures, while theorems of analysis and topology are restricted to separable spaces. Many principles that imply the axiom of choice in their general form become provable in weak subsystems of second-order arithmetic when they are restricted. For example, every field has an algebraic closure is not provable in ZF set theory. But the restricted form, every countable field has an algebraic closure, is provable in RCA0, the weakest system typically employed in reverse mathematics. The big five subsystems of second-order arithmetic. Second-order arithmetic is a formal theory of the natural numbers and sets of natural numbers. Many mathematical objects, such as countable rings, groups, and fields, as well as points in effective Polish spaces, can be represented as sets of natural numbers, and modulo this representation can be studied in second-order arithmetic. Reverse mathematics makes use of several subsystems of second-order arithmetic. A typical reverse mathematics theorem shows that a particular mathematical theorem T is equivalent to a particular subsystem S of second-order arithmetic over a weaker subsystem B. This weaker system B is known as the base system for the result. In order for the reverse mathematics result to have meaning, this system must not itself be able to prove the mathematical theorem T. Simpson describes 5 particular subsystems of second-order arithmetic, which he calls the Big Five, that occur frequently in reverse mathematics. In order of increasing strength, these systems are named by the initialisms RCA0, WKL0, ACA0, ATR0, and Pi11CAO. The following table summarizes the Big Five systems. Simpson. The subscript 0 in these names means that the induction scheme has been restricted from the full second-order induction scheme. For example, ACA0 includes the induction axiom NNX. This, together with the full comprehension axiom of second-order arithmetic, implies the full second-order induction scheme given by the universal closure of n-phi for any second-order formula phi. However, ACA0 does not have the full comprehension axiom, and the subscript 0 is a reminder that it does not have the full second-order induction scheme either. This restriction is important. Systems with restricted induction have significantly lower proof theoretical ordinals than systems with the full second-order induction scheme. The base system RCA0 is the fragment of second-order arithmetic whose axioms are the axioms of Robinson arithmetic, induction for sigma 01 formulas, and comprehension for delta 01 formulas. The subsystem RCA0 is the one most commonly used as a base system for reverse mathematics. The initials RCA stand for recursive comprehension axiom, where recursive means computable, as in recursive function. This name is used because RCA0 corresponds informally to computable mathematics. In particular, any set of natural numbers that can be proven to exist in RCA0 is computable, and thus any theorem which implies that non-computable sets exist is not provable in RCA0. To this extent, RCA0 is a constructive system, although it does not meet the requirements of the program of constructivism because it is a theory in classical logic including the excluded middle. Despite its seeming weakness, RCA0 is sufficient to prove a number of classical theorems which, therefore, require only minimal logical strength. These theorems are, in a sense, below the reach of the reverse mathematics enterprise because they are already provable in the base system. The classical theorems provable in RCA0 include basic properties of the natural numbers, integers, and rational numbers, basic properties of the real numbers, the bare category theorem for a complete separable metric space, the intermediate value theorem on continuous real functions, the Banach-Steinhaus theorem for a sequence of continuous linear operators on separable Banach spaces, a weak version of Gödel's completeness theorem, the existence of an algebraic closure for a countable field, the existence and uniqueness of the real closure of a countable ordered field. The first-order part of RCA0 is the set of theorems of first-order Peano arithmetic with induction limited to sigma 01 formulas. It is provably consistent, as is RCA0, in full first-order Peano arithmetic. Weak Koenig's lemma WKL0. The subsystem WKL0 consists of RCA0 plus a weak form of Koenig's lemma, namely the statement that every infinite subtree of the full binary tree has an infinite path. This proposition, which is known as weak Koenig's lemma, is easy to state in the language of second-order arithmetic. WKL0 can also be defined as the principle of sigma 01 separation. The following remark on terminology is in order. The term, weak Koenig's lemma, refers to the sentence which says that any infinite subtree of the binary tree has an infinite path. When this axiom is added to RCA0, the resulting subsystem is called WKL0. A similar distinction between particular axioms, on the one hand, and subsystems including the basic axioms and induction, on the other hand, is made for the stronger subsystems described below. In a sense, weak Koenig's lemma is a form of the axiom of choice. It is not constructively valid in some senses of the word constructive. To show that WKL0 is actually stronger than RCA0, it is sufficient to exhibit a theorem of WKL0 which implies that non-computable sets exist. This is not difficult. WKL0 implies the existence of separating sets for effectively inseparable recursively enumerable sets. It turns out that RCA0 and WKL0 have the same first-order part, meaning that they prove the same first-order sentences. WKL0 can prove a good number of classical mathematical results which do not follow from RCA0. However, these results are not expressible as first-order statements but can be expressed as second-order statements. The following results are equivalent to weak Koenig's lemma and thus to WKL0 over RCA0. The Heine-Borel theorem for the closed unit real interval, in the following sense. Every covering by a sequence of open intervals has a finite subcovering. The Heine-Borel theorem for complete totally bounded separable metric spaces. A continuous real function on the closed unit interval is bounded. A continuous real function on the closed unit interval can be uniformly approximated by polynomials. A continuous real function on the closed unit interval is uniformly continuous. A continuous real function on the closed unit interval is Riemann integrable. The Brouwer fixed-point theorem. The separable Hahn-Banach theorem in the form. A bounded linear form on a subspace of a separable Banach space extends to a bounded linear form on the whole space. The Jordan curve theorem. Gödel's completeness theorem. Determinacy for open games on 0, 1 of length omega. Every countable commutative ring has a prime ideal. Every countable formally real field is orderable. Uniqueness of algebraic closure. Arithmetical comprehension ACA0. ACA0 is RCA0 plus the comprehension scheme for arithmetical formulas. That is, ACA0 allows us to form the set of natural numbers satisfying an arbitrary arithmetical formula. Actually, it suffices to add to RCA0 the comprehension scheme for sigma 1 formulas in order to obtain full arithmetical comprehension. The first-order part of ACA0 is exactly first-order Peano arithmetic. ACA0 is a conservative extension of first-order Peano arithmetic. The two systems are provably equiconsistent. ACA0 can be thought of as a framework of predicative mathematics, although there are predicatively provable theorems that are not provable in ACA0. Most of the fundamental results about the natural numbers, and many other mathematical theorems, can be proven in this system. One way of seeing that ACA0 is stronger than WKL0 is to exhibit a model of WKL0 that doesn't contain all arithmetical sets. In fact, it is possible to build a model of WKL0 consisting entirely of low sets using the low basis theorem. Since low sets relative to low sets are low, the following assertions are equivalent to ACA0 over RCA0. The sequential completeness of the real numbers. The Bolzano-Weierstrass theorem. Ascoli's theorem. Every bounded equicontinuous sequence of real functions on the unit interval has a uniformly convergent subsequence. Every countable commutative ring has a maximal ideal. Every countable vector space over the rationals has a basis. Every countable field has a transcendence basis. Koenig's lemma. Various theorems in combinatorics, such as certain forms of Ramsey's theorem, arithmetical transfinite recursion ATR0. The system ATR0 adds to ACA0 an axiom which states, informally, that any arithmetical functional can be iterated transfinitely along any countable well-ordering starting with any set. ATR0 is equivalent over ACA0 to the principle of sigma 11 separation. ATR0 is impredicative, and has the proof-theoretic ordinal, the supremum of that of predicative systems. ATR0 proves the consistency of ACA0, and thus by Gödel's theorem it is strictly stronger. The following assertions are equivalent to ATR0 over RCA0. Any two countable well-orderings are comparable, that is, they are isomorphic or one is isomorphic to a proper initial segment of the other. Ulm's theorem for countable reduced abelian groups. The perfect set theorem, which states that every uncountable closed subset of a complete separable metric space contains a perfect closed set. Lausson's separation theorem. Determinacy for open sets in the Baire space. Pi11 comprehension Pi11 CAO. Pi11 CAO is stronger than arithmetical transfinite recursion and is fully impredicative. It consists of RCA0 plus the comprehension scheme for Pi11 formulas. In a sense, Pi11 CAO comprehension is to arithmetical transfinite recursion as ACA0 is to weak Koenig's lemma. It is equivalent to several statements of descriptive set theory whose proofs make use of strongly impredicative arguments. This equivalence shows that these impredicative arguments cannot be removed. The following theorems are equivalent to Pi11 CAO over RCA0. The Cantor-Bendixson theorem. Every countable abelian group is the direct sum of a divisible group and a reduced group. Additional systems. Weaker systems than recursive comprehension can be defined. The weak system RCA*0 consists of elementary function arithmetic EFA plus delta O1 comprehension over RCA*0. Recursive comprehension as defined earlier is equivalent to the statement that a polynomial has only finitely many roots and to the classification theorem for finitely generated abelian groups. The system RCA*0 has the same proof-theoretic ordinal omega-3 as EFA and is conservative over EFA for Pi02 sentences. Weak Koenig's lemma is the statement that a subtree of the infinite binary tree having no infinite paths has an asymptotically vanishing proportion of the leaves at length n. An equivalent formulation is that any subset of Cantor space that has positive measure is non-empty. WWKL0 is obtained by adjoining this axiom to RCA0. The model theory of WWKL0 is closely connected to the theory of algorithmically random sequences. DNR adds to RCA0 an axiom asserting the existence of a diagonally non-recursive function relative to every set. That is, DNR states that, for any set A, there exists a total function f such that for all E the th partial recursive function with oracle A is not equal to f. DNR is strictly weaker than WWKL. Delta 11 comprehension is in certain ways analogous to arithmetical transfinite recursion, as recursive comprehension is to weak Koenig's lemma. It has the hyperarithmetical sets as minimal omega model. Arithmetical transfinite recursion proves Delta 11 comprehension, but not the other way around. Sigma 11 choice is the statement that if eta is a sigma 11 formula such that for each n there exists an x satisfying eta, then there is a sequence of sets xn such that eta holds for each n. Sigma 11 choice also has the hyperarithmetical sets as minimal omega model. Arithmetical transfinite recursion proves sigma 11 choice but not the other way around. Omega models and beta models. The omega in omega model stands for the set of non-negative integers. An omega model is a model for a fragment of second-order arithmetic whose first-order part is the standard model of Peano arithmetic, but whose second-order part may be non-standard. More precisely, an omega model is given by a choice S2 omega of subsets of omega. The first-order variables are interpreted in the usual way as elements of omega, and plus times have their usual meanings, while second-order variables are interpreted as elements of S. There is a standard omega model where one just takes S to consist of all subsets of the integers. However, there are also other omega models. For example, RCA0 has a minimal omega model where S consists of the recursive subsets of omega. A beta model is an omega model that is equivalent to the standard omega model for pi11 and sigma11 sentences. Non-omega models are also useful, especially in the proofs of conservation theorems.